Welcome to the second lecture of Control System 2. So today we are going to discuss about the introduction to state space representation. Let us recall the last lecture what we have discussed. We have discussed the several properties of a dynamical system like linearity, like time invariancy. Then we have discussed that some drawbacks are there for transfer function modeling. So what are the drawbacks are there for the transfer function modeling? A transfer function is only defined under zero initial condition, and also in the last class I told that the nonlinear system cannot be modeled using transfer function approach, but which is not true. Actually, the transfer function modeling can be done for a nonlinear system. For that, nonlinear system has to be linearized about its equilibrium point, and then the linearized system can be represented using transfer function approach. Okay, and most importantly, we have pointed out that the transfer function technique reveals only the system output for a given input and provides no information regarding the internal state of the system. So we want to understand today's lecture that that if for a system, if we will assume zero initial condition, then it may leads to a wrong decision about the system response, and which is very much related with the understanding of internal state of the system. So that's why in this lecture we are going to understand that what do you mean by the internal states of the system, and slowly we will give the answer of that all these question subsequently. Okay, what are the state space model? Once we will understand that for a system what are the states, then definitely we will try to understand that what are the state space models are and why should we use them, and also how to develop a state space model for a dynamical system. So let us come back to our today's discussion, that is introduction to state space representation. So these will be the outlines for that we will discuss about the introduction. Then we will try to discuss about the concept of state variable and state model. Then some of the motivating example we will discuss by which we will able to understand this state variable and state model. We will take the example of mechanical and electrical network. Then formally we will define the state vector and state space, and definitely I will show you several references from where I prepare these slides. So now I'm going to show you some conceptual model of a system, that where we regard a system as consisting of inputs. So there are R number of inputs are there, U1, U2, UR. As I told you that we want to go for a generalized modeling technique where a MIMO system also can be modeled. Okay, so that's why here I have taken, or we are considering a system where R number of inputs are there and there are M number of outputs. They are denoted Y1, Y2, Ym, and some of the state variables we are denoting x1, x2, xn, means n number of state variable or internal variables we have assumed. But at this point you may not understand what do you mean by the internal states, but just you assume that some variables are there other than inputs and outputs in a system exist. That only you try to understand now, and subsequently I will definitely discuss what do you mean by the internal variable or state variables. So till now for the transfer function modeling we have understood that system having the set of inputs and it is producing set of outputs. We never understood about, or I never told about the internal or state variables, but now I am claiming that along with the inputs and output we are considering some of the internal variables or state variables of the system, which are denoted by x1, x2, xn. So now we are discussing multiple input, multiple output, and there are n number of state variables we are considering. So to represent it, we are using vector notation because it will be easy to represent, because we have r number of inputs. So how we will represent them? So it will be easy for us if we will use the vector notation to represent them. So here you see y is a vector which having m number of component, that is y1, y2, ym. So the size of this vector, actually the m cross 1. Okay, and now the input having r number of inputs, so we have represented r number of input in a column vector, and that vector is represented by u. Okay, u having a r number of components, so this is r cross 1. Okay, and the n number of state variables are there, so we have represented by n number of component of the state variable x. So the dimension of this x vector is n by 1, n number of rows, 1 column. Okay, so denote the m output vector and r input vector u, and x is the n state vector. Fine. So for example, in a circuit, y and u might represent terminal voltages and input voltages, and x the vector, the internal currents and voltages across all branches. So here just a rough idea I have tried to give, that what do you mean by the internal states or the state variables. Fine. Considering human body, the inputs may be food intake, beverages consumed, and medication administered, and the output y may be body temperature, blood pressure, pulse rate, while the internal variable x may be heart rate, blood sugar concentration, brain activity level, and various hormones levels. So while we are dealing with our human body, so only the input output behavior is not sufficient. We have to consider the internal, what are the effects in the internal variables when we are analyzing the input output behavior. So along with the input output behavior, we must know that what are the internal variables present in a system, how they are evolving with respect to time. Okay, so but more clearly we will discuss about the internal variables when we will take a particular example. So that's why here you see one conceptual model have for a dynamical system have been represented. We have r number of inputs, so these are the inputs to the system, and these are the inputs to the system, and y1, y2, ym are the outputs, m number of outputs of the system, and we have some internal variables or state variables which are represented by x1, x2, and xn. Now we have learned about transfer function representation in the last course. Analysis of systems and synthesis of controllers have been done based on this representation, that is transfer function. To represent the dynamical system using transfer function requires to identify outputs and inputs. Means, so when I will give you a system and I will ask that find the transfer function for the system, then what you will do, you will find that, or you will ask what are the inputs, or what is the, if it is a system, you will ask what is the input to the system, then you will ask what is the output of the system. Once the input and output is identified for a given dynamical system, then you will apply the fundamental laws to find out the differential equation which is described, which will relate the input output, and also which will describe the dynamics of the system, and then applying the Laplace transform, you will find out the transfer function, and you will assume that all initial conditions are 0. So most important thing to build the transfer function for a system, you will identify what are the inputs and what are the outputs. Okay, and that's why it is written that along with identifying the outputs and inputs, while deriving the transfer function of the system, you will also assume that all initial conditions are 0. But in contrast to that, when you are going to represent the system using state space, which is a time domain approach, you require to identify inputs, outputs, also the state variable. So these three things has to be identified to build the state space representation of a given system. Okay. Now, why do we need state variables? So it is very important in this point to ask, okay, previously we are knowing the inputs and outputs and we are building the transfer function. Then why the extra variable, that is state variables or internal variables of the systems, are to be identified? Why it is required? So another question, obvious question is coming into our mind: what wrong can happen if we always assume initial conditions of a dynamical system 0? So that also need to be understood. And after that, it is coming in our mind, are these initial conditions are related to state variable or internal variables? Are these initial conditions which we are assuming 0 and which is present in the and which is we are telling that extra state variable has to be identified. State variables are to be identified for a given system. Are they anyhow related? Means these initial conditions and the internal state variables or internal variables are related. So let us discuss this answer of this question, or to find out or to get the answer of this question. Let us discuss in the following way. So that's why, to understand these things, that why we need the state variables, what wrong can happen if we always assume initial condition of a dynamical system 0, or are these initial conditions are related to the state variable or internal variables, we are considering a motivating example. So in this example, we have taken a system with a transfer function h of s is equal to 1 by s minus 1. So this is the pictorial representation. So we have taken a system. So this is the system h of s, and whose transfer function is 1 by s minus 1. U is the input and y is the output. So from the representation, you can understand that it is a unstable system. Why it is an unstable system? Because the pole of the system is located at the right half of the s plane, that is s equal to plus 1. So definitely it is a unstable system. To stabilize it, we can precede HFS with a compensator, and the compensator transfer function is s minus 1 by s plus 1. So now we are finding that s minus 1 is a pole, s minus 1 means s equal to plus 1 is an unstable pole. So now to stabilize this system, we have cascaded a controller with a transfer function s minus 1 by s plus 1. So what will be the overall transfer function for the system? The overall transfer function for the system will be 1 by s plus 1. So if it is 1 by s plus 1, so definitely the system will be, the overall system will be stable. Why? Because suppose if we will consider the overall system, so the overall system now consists of two things, that is the controller and the system. So now the overall transfer function, we are finding that ys is the ys is the output and vs is the input. So now that is simply 1 by s plus 1. Fine. Now if we want to find out that y of s from here, so it will be 1 by s plus 1 into vs. Okay. Now from here it is very much clear that if we want to find out the y of t from here, that will be e to the power minus t into not into, when these two signals are in multiplication in frequency domain, then it will be convoluted. So convolution of v of t, which is the input to the system. Now from here it is very much clear, for a bounded input the output will be always bounded. Why? Because the e to the power minus t will be going to decrease as T will be sufficiently large. So in this way we are claiming that the overall system will be stable. Okay, means we want to say that the overall system will be Bibo stable. So this is a nice outcome. The overall system looks stable. To verify, let us try and simulate this system on an analog computer. So now what we want to do, that we want to verify that really the system is stable or not. To do that one, we want to implement this overall system, means the subsystem wise in a laboratory. Fine, and we will try to take help of a analog computers to implement that. So what do you mean by the analog computers? Who is doing the analog computing? Means by receiving the analog signal, the computation has been done and it is producing the another analog signal after the computation. Who are doing that job? The operational amplifier. So now we will try to implement these subsystems to get the overall system in the laboratory using operational amplifier. And my claim is that unfortunately this technique will not work. Which technique will not work? Not to the stabilization of the system. What we are looking, that the output of the system is going to be decreased. This technique will not work. After a while the system will tend to burn, or the output YT saturate. Means if we will connect a CRO at the output, then for a given input, for a bounded input, we will see that instead of decreasing, or instead of we are getting the bounded output, we will get a unbounded output for this given system. So that investigation we have to do, so why this can happen, and whether my claim is true or not. So to do that one, we will try to implement this system using operational amplifier. Then the question is that what are the building blocks required from the operational amplifier? We will use three main components. The three components are the integrator. We will use integrator. So now you know that using operational amplifier, easily the V out will be the integration of V in, so which is represented that by a block. This is the integrator sign. So here, if it is not clearly visible, so this is the integration sign. So if you give the V in a voltage signal, your output will be integrated. Okay, now we will use another component that is called gain amplifier. So this is a amplifier using operational amplifier. Now if you give a V in, we will get a output which is K times. So K is the amplifier gain. And another component we are going to use, that is called adder. So we have several voltage signal V1, V2, Vn. If we have a adder circuit, these voltage signals will be added, and V out will be the addition of V1, V2 plus Vn. So my intention is that using these three components, that is integrator, gain amplifier and adder, we will develop this system. We will develop this system in the laboratory. Then the question is how we can do that one. To do that one, we have to represent this system in time domain. Then it will be easy for us to simulate this circuit in the laboratory using the components like integrator, gain amplifier and adder. So then we will try to represent this system in time domain as a subsystem wise. So we will take we will consider this HCS one subsystem, that is S minus 1 by S plus 1, and another subsystem we will consider HFS, that is 1 by S minus 1. So let us try to see that if each subsystem is represented in time domain, how they look. So now that's why we have considered that HC of S, that is the ratio of US by VS, that is yes, US by VS, that is, no, actually I did a mistake here. HCS is what? The HCS is, yes, it is correct, US by VS. Sorry, it is correct. So US by VS, that is S minus 1 by S plus 1. So now we will cross multiply and we will get US into S plus 1 equal to Vs into s minus 1. And now if we take the inverse Laplace transform, then we can represent the signal in time domain, because it is s into us, so it will be first derivative of ut, then here you will get Vs into Vs, so it will be v dot t is equal to minus ut minus Vt. And the second subsystem having the transfer function, that is y of s by us, that is 1 by s minus 1. If we will cross multiply, we will get y of s into s minus 1 equal to s us. And if you represent the system in time domain using inverse Laplace transform, it will be y dot of t minus yt equal to ut. Okay, now we will focus mainly using this with this two equation, that is equation number 3 and the equation number 5. So these two equation we will consider. So now to represent this two time domain equation in a more compact form, we will use some of the variables. Okay, so let us define some of the variables. We will know that for this system, input is Vt and output is Yt. Along with that, I am giving the name of the following variables. Just I am giving name here. Try to understand that ut minus Vt, this expression ut minus Vt, or this variable, we are assuming or we are giving a name, that is x1 of t, and another system variable, that is the output yt, we are giving another name, that is x2 of t. Okay, so these are the by definition ut minus Vt, I have given a name, that is x1t, and yt, what is the fortunately yt is the output for the system, we have given another name, x2t. Now these two equations, that is equation number 3 and equation number 4, we will try to write with these variables only, that is x1t, x2t and Vt. Okay, and the system output we will write yt. So with these variables we will try to represent equation number 3 and equation number 5. So from the equation number 3, that we can write that, you see it is what is the relation, it is minus ut minus Vt. So the same thing can be written minus ut plus Vt minus of 2 Vt. Now if we will take minus common, then ut minus Vt, and as per our assumption or definition, ut minus Vt is represented by x1, so I can write minus x1 of t and minus 2 Vt. So this is the first equation we got, that x1 dot t is equal to minus x1t minus 2 Vt. So similarly the equation number 5, so this is the equation number 5, y dot t minus yt equal to ut, we will write in this way, y dot t equal to ut plus yt, and then again we have written minus Vt and plus Vt. So ut minus Vt is x1 and yt we have defined x2 plus Vt. Now you see the same system, that is equation number 3, and which is represented by equation number 3 and 5. Now using these variables we have represented in another form, which is certainly the two first order differential equation, where we have expressed at the right hand side of this equation only with this variable either x1 and x2 and the input Vt. So now the overall system can be represented by these two subsystem, that is x1 dot t is equal to minus x1t plus 2 minus 2 Vt, and x2 dot t is equal to x1t plus x2t plus Vt. So these are the two differential equation which is representing the system. And what is the system output? Now output is yt equal to x2t. Fine. So yt is x2t. So this is the description of the system what we have taken in the frequency domain, and this is the representation of the system in time domain. And now our intention is that to implement these two differential equation in the laboratory using the components like integrator, amplifier gain, and the summer or So now you see that we have tried to represent the system in the following way. You see, first equation I am representing that x1 dot t is equal to minus x1 minus 2 vt, where vt is the input. So we will start with the input. So we have started with the input. You see, this is the input vt. Now vt is multiplied. So now vt, you can see that now Vt is multiplied with the gain minus 2. So now you come to know that using amplifier gain, how can we realize minus 2? So that minus 2 is there, and now you are finding that this minus 2 Vt has to be added with minus x1. But how we will get x1? Now if we have a x1 dot, if we integrate it, then as a solution we will get x1, and then we can feedback it. So now you see the x1 dot is equal to minus 2 vt and minus x1. How we will get that x1? Now x1 dot has to be integrated, and then we will get the x1. So now this is the first subsystem we have represented, where we are getting x1 as a one variable what we have defined. Now we want to represent the second subsystem, that is x2 dot equal to x1t plus x2t plus vt. So now similar way, so we require x1t. So from the first system we are getting x1t. So this is this from here we are getting x1 t, and now we have to add vt. So from here with a gain 1 we are getting vt. So here we are getting vt, but how we will get? So this is x1t and this is vt. So now we will get, how we will get x2t? Now x2t we will get if we will integrate x2 dot. So now x2 dot is integrated to get x2, and now x2 is multiplied with a gain 1, and it has been added with the signal vt plus x1t and x2t, that is equal to x2 dot t. So now you see how using the adder, then gain and the integrator, how we have implemented the system what we have represented in frequency domain. Okay, so now here you are finding that the system output is also available. Why the system output how the system output y is available? Because x2 is already, we have defined that x2 is equal to y. So now these are the two subsystems cascaded, and in this way the system can be implemented in the laboratory. And now suppose we want to start the simulation, okay, or we want to start the experiment. So now if we want to start the experiment, what additional information we require? Immediately after building this block, actually we cannot start the simulation or the experiment. We require some other information. What are they? So to understand these things, we will try to try to answer this question, that what are the additional information is required to start the simulation or to start the experiment. We will try to answer this question in a different way. Let us understood in this way that that it can be readily verified that these simulations have the desired transfer function. Okay, so you can check the overall transfer function for this system is still that ys by vs, means the transfer function, if you find out, that is the overall transfer function ys by vs is still it is 1 by s plus 1. If you want, you can verify. If you actually implement this analog computer in laboratory, you will find that the output Y saturates or the system burnouts. That already we have claimed, and we want to establish that. Okay, the overall transfer function 1 by s plus 1 did not say anything about that, but we from the transfer function we cannot predict that one. We are observing that from the transfer function, for any bounded input always output will be bounded. But my claim is that if you actually implement this circuit in the laboratory, output is going to be saturated, means that the output for any bounded input are going to be increased unboundedly. Okay, so that has to be established. To find out why this happens, look at the differential equation involved in the diagram above. So that thing what I'm telling, that if you really want to start the simulation, that some additional information is required. What are they? Now I will give the answer of that one. Okay, so another thing is important to note down here. To analyze the behavior of this realization, it is natural to consider the evolution of the major variables in the realization, which are clearly the integrator output, say the x1t and x2t. It is to be noted that the output of the system yt equal to also equal to x2t. Means if you want to know that how the output is going to be varied with respect to time, that time also you have to know the x2t. So mathematically, if you want to see that we have a set of differential equation, from there I want to know how the output is going to be varied over the time for a given input. So then if we want to know the output yt, means we have to solve x2t. We have to solve x2t, means a set of differential equation is given. To know the x2t, we have to solve the differential equation. Now it is very clear to understood that if we want to solve this differential equation, these inputs are not sufficient. Even if these inputs are given, you cannot solve this differential equation. What else is required to solve this differential equation? You require the initial conditions of the x1t and x2t. Means you require what is x1 of 0 and you require what is x2 of 0. These two informations are required to solve the differential equation. And in practice, how you will relate these things? Now, if you want to start the simulation, then actually you have to give the information in this integrator. You have to give this information to the integrator. This integrator needs the information about the x1 of 0, otherwise you cannot start the simulation. And also this integrator needs the information of x2 0, otherwise you cannot start the simulation. Okay, so this is the relation between mathematical realization and the practical. Okay, so now that's why in my next slide it has been discussed that to solve this differential equation, we need to know the initial condition x10 and x20. Suppose x10 is equal to x1 of 0, which is definitely a non-zero quantity, and x20 is assumed that x of 20, which is also not equal to 0, some non-zero quantity we have assuming. So it is not a 0. So how to solve this differential equation? Suppose now these initial conditions for the two variables x10 and x20 are given. Now how we can solve this differential equation, what we have represented by equation 8a and 8b. So now one procedure is that, easy procedure is that you use the Laplace transform technique to solve this differential equation. So we will use the Laplace transform technique to solve this equation. So you will taking the Laplace transform of equation 8a, we can find out what is x1 of s. Similarly, we can, taking the Laplace transform of equation 8b, we can find out what is x2 of s. Fine. And here, as we have assumed that the initial condition of x1 of 0 is x1 of 0, so that we have replaced, and x2 of 0 is x of 2 0, so that also we have replaced. So now our intention is to know what is the output. So output is x2s, and x2s you are finding that depends on x1 of s. So I have replaced the expression of x1 of s in the expression of 11. So if you replace the x1 of s in 11 by 10, ultimately the output expression y of s will be equal to this. So now our intention was to know what is the output. Okay, so now output, if you calculate in time domain by taking the inverse Laplace transform of equation 12, then you will find that the inverse Laplace transform of equation 12 is essentially y2t, which is x2t, is equal to e to the power t x2 of 0, because it is s minus 1. And then if you do the partial fraction expansion of this term, then you can easily take the inverse Laplace of this this term, and you will get that you are getting half of e to the power t minus of e to the power minus t x1 of 0 plus e to the power minus t convolution of vt, because vs is also a variable which is input variable of the system. So now you closely observe this equation number 12, you are finding that no longer, if even if suppose even if this input vt is bounded, the output is no longer bounded, because it is going to grow due to the term e to the power plus t x2 of 0, and also here half e to the power t x1 of 0 is present. Due to this two term, what will happen, even if your input is bounded, the output is going to be unbounded. So that's why here we have to understand that the transfer function didn't tell that. Why transfer function didn't tell that? Because in during evaluation of the transfer function, we have assumed x2 of 0 and x1 of 0 is equal to 0, these two initial condition. So this initial condition we have assumed 0, and this initial condition is assumed 0. And once you will assume these two initial conditions are 0, even if you are going, your output is going to be unbounded, it is not revealed by the transfer function approach. Only you can observe the term, that is e to the power minus t convolution of vt, and that's why you have concluded by looking at the transfer function that for a given bounded input, output always will be bounded. At that time these two terms were disappeared, these two terms were not appeared in the transfer function. That's why transfer function didn't tell about the fact that ultimately the output will be going to be unbounded if you assume any non-zero initial condition. So that's why the actual transfer function matches with the original only when x10 is equal to x20 equal to 0, but it is not possible to keep the initial condition for this dynamical system always equal to 0. So unless the initial condition can always be kept 0, yt will grow without bound. That is very important. Almost all initial condition will excite the unstable mode of oscillation. So that's why it has been claimed that whenever you will implement the circuit in the laboratory, the output yt, if you connect a CRO at the output, you will find that output is going to be saturated and the output will grow unboundedly, and it may burn the circuit. So that's why we have understood that the fact which is not revealed by the transfer function but by the analysis, the finer analysis have shown that if we will what wrong can happen if always we will assume that initial conditions are 0. Okay, so it may leads to the disaster. So it is concluded that we need a more generalized approach where we have a flexibility that we can assume any non-zero initial condition. So that's why we need a more generalized representation of a system where we can accommodate in the analysis or accommodate accommodate in the representation that initial conditions. Okay, and here one very interesting thing we want to discuss, that for what initial condition the output does not saturate. Other than 0, some initial conditions still exist for which the output is not going to be saturated. What are they? Now you see this star, that e to the power x20 and half of e to the power t x1 of 0. These two terms actually creating problem because these two terms are growing unboundedly. So if we cancel this two term, then what will happen? Then the output is going to be bounded for a bounded input. So how we can cancel that? Now we can equate them. E to the power t x2 of 0 is equal to negative of half e to the power t x1 of 0. And if you solve that, we are finding that x1 of 0 minus 2 of x20. So if you able to select the special initial conditions, that is x1 of 0 is negative of 2 times of x20, for this initial condition only the output will be bounded. Other than that, all initial condition the output is going to be unbounded. So that's why it is written almost all, except this initial condition, almost all initial condition will excite the unstable mode of oscillation. So now I think with this lecture it has been clear that if we will assume that all initial conditions are zero for a given system, that what wrong can happen with the system. And also here one important thing is clear, that we need to represent the system along with the input output some internal variable, which is here actually the x1t x2t. So that's why here you see I told that let's call x1t x2t are the states. So these states x1t and x2t, whose initial conditions are actually required to be known. Otherwise what will happen if you assume that these initial conditions are zero, which may lead to the disaster or wrong decision. So formally I have not defined the state variables, but just to think about, or just to give a light on that we found that these two variables are very important, which are the output of the integrators, are very important to give the decision, because we found that their initial conditions are if not equal to zero, then the output is going to be unbounded. So that's why at the end of this discussion we can say that internal behavior of the systems are complicated. Transfer function cannot describe the internal behavior. Why? Because transfer function only looks the input output behavior. So what the input has been given, for that what will be the output. It is not going to consider the internal dynamics or internal behavior of the system, which is complicated, so which is not revealed by the transfer function. So we require a more generic representation of the system, which is known as state space representation. So in the next class, I will continue with some motivating example, that how you will define, or how you will find out the or how you will identify the state variables or internal variables of a given system. Thank you.